Welcome to clickmyproject.com. We will discuss about the product for critical path analysis and low complexity implementation of the LMS adaptive algorithm. Next, we will see the abstract for the product. Adaptive digital filter find wide application in several digital signal processing areas. Example for noise and echo cancellation, system identification, channel estimation, channel equalization, etc. The tapped delay line finite impulse response FAR filter, whose weighted are updated by the famous Windrow-Hoff least mean square LMS adaptive algorithm, may be considered as simplest known as adaptive filter. The LMS adaptive filter is the popular not only due to the low complexity but also due to the stability and satisfactory conventions performance level. Due to its several important application, current relevance increasing the constraint on area, time and power complexity, efficient implementation of LMS adaptive filter. This paper proposes a precise analysis of the critical path of the least mean square adaptive filter for deriving its architecture for a high speed and low complexity implementation. It's shown that the direct form of LMS adaptive filter has nearly same critical path as it is transparent from counterpart but provides much faster convenience and low register complexity. From the critical path evaluation, it's further shown that no pipelining is required from the implementing the direct form of LMS adaptive filter for most particular cases can be realized with a very small adaptation delay in case of whether a very high sampling rate is required. Then we will see the flow diagram for the product. The input samples and the error samples to apply the delay unit architectures. The delay unit architecture is mainly based on the register element. The develop register elements to use the delay adder process. Then the delay element result is applied to the partial border generation unit. The error bit samples is to create the error coefficient manner. Thus, add the addition work to the error input bit samples using the partial border generation architecture. The partial border generation addition architectures mainly based on the carry select addition process. Then to apply the shift add architecture block. The partial border generation result is to pass the shift add architecture block. The shift add architecture block is used to the addition the partial border generation results in separate manner. This process is mainly used to the reduce the carry propagation time and to reduce the hardware complexity for the shift add architecture work. Then the shift add architecture result is applied to the delay and adder element. The delay and adder element mainly used for the store the results in register, then to apply the final output results. The final output results to get the delay and adder element. The delay element is mainly used for the flip-flop register element. The adder element is mainly focused by the LSB and MSB position for the shift add architecture result and to apply the delay and adder unit elements. The final output samples is mainly based on the synthesis and simulation results elements. The simulation results is mainly passed by the binary results element and the synthesis report is mainly focused by the satisfy the parameter results for the our architecture. And finally we see the output for the product. First of all, we open our processing folder, then we open the Xilinx ISC project. Our program is developed in VHDL language. Then we select the waiter update block to select the simulation work. Then to select simulate behavioral model. We run the process for our processing result, then open the Xilinx ISM projects. The simulation behavioral model was completed successfully. Then create the ISM project list. Then we apply the binary input and to calculate the output weighted bits. Now apply the 16-bit data length for our project. Then add the error signal in coefficient manner. Then apply the clock pulse. We can create the programmable process. Just we close the simulation process. Next we go into this implementation work. The implementation work to create the view RTL schematic. Just we run the schematic diagram. The RTL schematic diagram is mainly used to create the RTL diagrammatic representation. Just we double click this diagrammatic representation is mainly used to what are the logical blocks is placed in our weighted filter architecture. Then the technology diagram is represents the what are the lookup table and input output buffers, then wire connections and flip-flop pairs to be applied by the our overall weighted filter architecture. Then we go to the design summary result, then the synthesis report. Just we generate the synthesis report for the weighted filter architecture. This architecture results is to calculate the area of the device utilization of weighted filter architecture, and finally we calculate the timing allocations for the latency and delay time calculation for our weighted filter architecture level.